Alrighty. Let's begin with a word of prayer. I'll start. Heavenly Father, we thank you for this day. And Lord, I thank you for the students. And I just pray that you'd guide my work today. Help us to glorify you, Lord, what we do. In your name we pray, Lord Jesus. Amen. So I just wanted to pick up on the solutions to the homework, talk about them a little bit more. So I think we got to, if I remember right, a few help sessions ago, I got to this problem, problem 94, basically to find the, let's see here, there we go. So to picture the ideal generated by 2 plus 2i in the Gaussian integers, I just made a picture with my graph paper, handy dandy graph paper, and essentially 2 plus 2i multiplied by an integer allows you to go in 4 different directions, because you also take sums of these. Anyway, long story short, you get 2 plus 2i, you get minus 2, minus 2i, you get 2i minus 2, you get minus 2i plus 2. These are all different things you can add to a given point, and those things are inside this ideal. So all the points connected by integer linear combinations of these guys are in the same coset. So graphically, this point, and 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 this point are all identified. So those form the coset I itself. And then like I plus 1 is this guy, I plus 2 is that guy, I plus 3 is that, here's I guess this is 2 plus I. Here's 2 minus I is that one. And so I just focused in a fundamental region here and identified one of each representative. Well, I guess there's 2 of each representatives for this guy and that guy, but for the interior ones, there's just a single representative for each one of these classes. Of course, this point would then be related to that point, which would then be related to that point, and so forth and so on. Okay, enough. Anyway, this picture graphically allows me to figure out that the Gaussian integers mod the principal ideal generated by 2 plus 2i has 8 things in it, and they're just these cosets I, 1 plus I, 1 minus I, ... There's 8 of them. Okay, so that's one problem. Next problem, we were asked to show that the quotient of the polynomials with z2 coefficients mod the principal ideal generated by x squared plus x plus 1 is a field. So basically, my approach was to say, hey, well, f of 0 is 1, f of 1 is 1. That means that it has no 0, so that's irreducible, right? So thus, f of x has no 0 in z2, and hence no linear factor, which means f of x is irreducible. So in terms of our current technology, that suffices to show that it's a field, because we know that irreducible polynomials generate maximal ideals, and consequently a ring mod a maximal ideal is a field. Now, when this problem was assigned, that was not an available solution, so what you were expected to do at this point in Gaussian was just to prove explicitly. Well, I first tried to show maximality directly, but that was not helpful. And then finally, I had the sense to look at Gaussian's hint, at which point it became obvious that, you know, I have these are my cosets, I, 1 plus I, x plus 1 plus I. Everything else can be reduced because we're setting x squared plus x plus 1 to be in the ideal. So we get these reductions like x squared plus I is x plus 1 times I. Anything quadratic or higher order can be reduced down to lower order stuff as usual. So I get these 4 cosets. And then I just figure out, okay, so first of all, 1 plus I serves as the identity in here. Okay, great. That's 0. To prove this is a field, I just have to show that the non-zero things, namely this, and that, have multiplicative inverses, but 1 plus I is its own inverse, so there's 1. And then, here's the proof that 1 plus I is 1. 1 plus I times that is a plus bx times I. So 1 plus I serves as 1. I think this is a general truth. If we have a ring with unity and we mod by some ideal, and that ideal does not contain the unity, then then the unity coset will serve as the identity, multiplicative identity for the quotient. Anyway, so x plus I times x plus 1 is x squared plus x, but x squared plus x is 1. So there you go. The product of this and that is the unity in the quotient. Consequently, this and this are inverses of each other, which then shows that all of the non-zero elements in this set have multiplicative inverses, which is to prove that Z2x mod I is in fact a field with 4 elements. Which, by the way, is pointed out later when we were studying field extensions. But, oh, this one was not bad. This one's pretty straightforward. I'll let you look at it. Oh, I guess I'll let you look at it again here. It's basically to prove that the ideal generated by A1 through AN is an ideal. We just use the ideal test, which is to show the difference is again in there, right? Y minus x is again in the ideal, given that x and y are in the ideal. And also that the product of something in the ideal and something in the ring is again in the ideal. So the Uber closure, if you will. All right, so that was basically the end of, what am I on? That was lecture 24 problems. Moving along here, lecture 25. This one. A few more solutions to look at. I think I covered this. No, I know I went over this with you guys already. So I'm going to go on. Let's see here. I'm going to go on. Yeah, I did that one too. I've already covered this one. Yes, I have. Can't remember. I tried to look at the previous things. I couldn't find where I did these, but I guess I did. All right, so I'll pick up here, lecture 27, solutions, problem 109. If I've skipped any, you'll forgive me, but then again, I mean, I have provided written solutions, so you can work through them. Of course, you know, it's not enough just to work through my solutions. You really need to come to an understanding of them for yourself. If you don't struggle with them, then you don't really learn them, you know. All right, so anyway, if f is a field, and we've got this polynomial, we're supposed to prove that x minus 1 is a factor if and only if the sum of these coefficients is 0. I look at this and I go, isn't this immediately obvious? But, I mean, fine, I think it is, but here's the proof. F of 1, right, if we evaluate at 1, we get this combination of the coefficients, which of course is the desired combination, and that's 0 because we're assuming that x minus 1 is a factor. X minus 1 is a factor implies by the factor theorem that f of 1 is 0. Consequently, this sum is 0. All right. Oh, I just did an if and only if. I guess I give an if and only if argument here. This is true if and only if f of 1 is equal to 0 and f of 1 is equal to 0, if and only if this is equal to 0. So this is that. X minus 1 is a factor if and only if the sum of the coefficients is 0. Yeah. That one was fun. This one, this one was more involved. Let R be a commutative ring with unity, I a prime ideal. Prove that I of x is a prime ideal of R of x. All right. So what I did to start with was I assumed, okay, I got prime ideal means the product, if the product's in the ideal, then either A or B is in the ideal, right? And I thought, okay, so to prove that I of x is a prime ideal, I should pick a product of polynomials being in the ideal and then work out why it is that either f of x or g of x has to be in the ideal. And so I started working on this, and I got a little ways into it, you know. I got a little ways into it because I don't know better. I mean, I tried it. So I took the product and multiplied it out, and I got some stuff, right? Like, so when you multiply it out, the constant coefficient c naught, right? So you got this constant coefficient. It's in the ideal, so that implies that either, well, it implies A naught's in the ideal or B naught's in the ideal, right? And then the next thing up, C1 would be A naught B1 plus A1 B naught. And then you can think about cases. If A naught's in the ideal, then that means that a naught b1 is also in the ideal, and that implies that the difference of c1 minus a naught b1 is in the ideal. Consequently, a1 b naught is in the ideal, which means then that, by the way, a1 or b naught is in the ideal. Anyway, this gets very old very fast, and you start to realize that this is definitely not the way to do this problem, because it is, I mean, I was starting to get somewhere, but it's just combinatorial and quite awful. So there's a much better way to do this problem, and it's as follows. So suppose I is a prime ideal of a commutative ring with unity R. It follows that R mod I is an integral domain. The natural homomorphism from R to the quotient, defined by pi of R is equal to R plus I, induces a natural homomorphism of R of X and R mod I of X. All right, by mapping the coefficients of R to the corresponding coefficients in the quotient. Let me show you that explicitly. Here's the homomorphism. I take a polynomial in R, and I map it to the corresponding quotient, polynomial with quotient coefficients, right, over here. And you can prove that, in fact, this is a homomorphism of rings. I may have some details down here. I forget what I did. Yeah, I mean, here's proof that it's additive. Yay, proof. And you can prove that it's multiplicative. I didn't bother. More interestingly, the kernel of this homomorphism is given by these polynomials such that this corresponding quotient coefficient polynomial is 0. So what does that mean? For this to be 0, that means that all of these coefficients must be 0, which means that a naught plus I is equal to I, and that an plus I is equal to I, right? Which is to say that a naught, a1, an is an I. Consequently, the kernel of psi is exactly the polynomials with coefficients from the ideal. Pretty awesome. And then also this a naught plus I, a1 plus I, an plus I, x to the n is mapped to that. This is mapped to by that, which this is arbitrary thing so anything of this form is mapped to by that. That means that psi, of course, is surjective because it hits everything in R mod I of X. So then we use the first isomorphism theorem of rings. And what's that give us? It gives us that R of X mod I of X is isomorphic to R mod I of X, because this is the image and that's the kernel of the psi mapping. Well, that's cool, because we know R mod I is an integral domain because I was prime. And that implies that R mod I of polynomials is also an integral domain, because we know that if we take a integral domain and look at polynomials over the integral domain, it's again an integral domain. But then this being isomorphic to that means that R of X mod I of X is an integral domain. Bammo. So we have that the quotient of R of X by I of X is an integral domain. That proves by our prime ideal theorem from back in the day that I of X is a prime ideal. This is an excellent problem. It uses much of the most important theorems that we've covered in this arc of the course. Very important problem to understand. All right, next problem. Let F be a field. You got two polynomials in the field. If there does not exist a polynomial of positive degree that divides both f of x and g of x, then prove that there exists h and k polynomials for which fh plus gk is equal to 1. So this is kind of the analog of Bazou's theorem, for it's the sort of greatest common divisor of polynomials kind of thing. So what you do is you construct this ideal, which is built in terms of polynomial combinations of these polynomials. Interesting. Like so. That's an ideal. I think we've proved that this is an ideal. The fact that this is an ideal is proved in the previous problem I was talking about today with the a sub 1 a sub n, proving that's an ideal. This is one of those forms with n equals to 2. Yeah. Now f of x is a principal ideal domain, which means that there has to be some j of x which generates this whole deal, right? And so you might notice that, in fact, if we put a of x equal to 1 and b of x equal to 0, as we can, because we can take the constant polynomials, that gives us that f of x, which has got to be, by the way, some multiple of j of x. So j of x divides f of x, and likewise g of x is obtained from 0 times f of x plus 1 times g of x, so it's in the ideal. But it's also got to be a multiple of j, so that means that j of x is divided by g of x. J of x divides g of x. So the generator of the ideal must divide both f and g. And as there does not exist, right, there does not exist j of x in f of x with the degree of x, degree of j greater than or equal to 1, that divides both these. I mean, this was assumed in the problem. That means that we must have the degree of j is 0. In other words, j of x is equal to a constant. So some constant has to generate f of x and g of x. Now, if c is equal to 0, that forces both f and g to be 0, which contradicts the assumptions of the problem. Consequently, c must be non-zero. And so if c is non-zero, then we can take and get that. Then we divide by c, and we get what we wanted, which was, here's my, what was it, k of x, and I forgot the letters, but there you go. There's the linear combination giving you back 1 like you wanted. And again, this is a polynomial analog to the GCD construction in the integers. Very nice. Construct a field of order 27. So basically, you just need to take z3x and mod by something that will make this a 3-dimensional vector space. Because if you have a 3-dimensional vector space over z3, it's got 3 to the 3, which is 27 things. So I chose this. I mean, there's other choices, I suppose, but this is irreducible over z3. Here's the proof. 0 goes to 2, 1 goes to 2, 2 goes to 2, so it doesn't have a 0. So this is irreducible. And remember that I can only do this non-zero test for order 2 or order 3, but this is order 3. If I was to do this for an order 4 thing, I would be outside my bounds, you know? We have that theorem that says order 2 and order 3 is irreducible if it has no zeros. Anyway, so mod 3, that's irreducible, so consequently this is a field, right? Because the irreducible polynomial generates a maximal ideal, and a ring mod a maximal ideal is a field. And then counting gives you 27. Number 113, determine which polynomials below are irreducible over Q. Well, yeah, so I used Eisenstein 3 because we got 3 divides 9, 12, 6, but 3 squared does not divide 6, so Eisenstein with p equal to 3 gives you irreducibility of this one. The next one, I couldn't apply Eisenstein, so I went back to my mod 2 reduction, and if you look at the induced polynomial with mod 2 coefficients, you get f bar of 0 is 1, f bar of 1 is 1, consequently it's irreducible over z2, which implies irreducibility over q. That was the theorem we had. X to the 4th plus 3x squared plus 3 is irreducible over q by p equals to the 3 application of Eisenstein. 3 divides 3, 3 divides 3, 9 does not divide 3, yay! Ah, Eisenstein, we love you. Anyway, so f of x, and this one I can't do Eisenstein, so I tried the z2 reduction, and bammo, it works again. There are ones where Eisenstein and z2 don't work, you know. That has happened. There are examples in Gaussian. We've looked at them. This one's a little bit more fun. 5 halves, 9 halves, 15, 3 sevenths, 6 and 3 14ths. So what I do is I multiply by 14 to make it prettier. And then once I do that, you can do Eisenstein. Because Eisenstein is for polynomials with integer coefficients. So if you want to do Eisenstein, you got to get a polynomial with integer coefficients. And the way to do that is to kill the fractions. The way to kill the fractions is to pick the least common multiple of the divisors in said polynomial. 2, 2, 1, 7, 14. Least common multiple, 14. Why we multiply by it. There you go. Yep. So Eisenstein 3 proves that 14 times f is irreducible. But if you could imagine a reduction of f, that would imply a corresponding reduction of 14 times f, but that's contradicting the unavailability of a non-trivial reduction. Consequently, that means f of x is also irreducible. This one, you guys kept asking me about this one before the break, and I refused, and I stand by my refusal. This one is very interesting. There's really quite a lot going on in this problem. And this is, we only really had maybe 5 problems this semester that I would say are genuinely difficult. This is one of them. So x to the 4th plus 1 is reducible over, there's conceptual difficulties in all your problems. I know you're learning, but I'm talking about, like, just nasty calculational trickiness. I think this has that. Anyway, so we want to show that this is reducible over ZP for any prime P. And what he argues is that in any prime P, you can solve one of these three equations. You either have an element such that a squared is minus 1. You've got an element that such that a squared is 2. Or you got an element such that a squared is minus 2. You've always got a solution to at least one of these equations in every possible Z mod P. I mean, so, well, obviously, right? No, I mean, come on, we're not alone. We do have the hint in Gaussian, which is I'm following and expositing, I hope. So, right. So anyway, in each of these three cases, given this condition, you can factor the polynomial as follows. Right? Like you've got x to the fourth plus 1. If a squared is equal to minus 1 mod p, then that's x to the fourth minus a squared, in which case that's, hey, this is supposed to be x squared minus a times x squared plus a. Sorry about that. But the point is it's a reduction, all right? So it factors. If a squared is equal to 2, then you can factor like this. I made a mistake. Anyway, and if a squared is equal to, and continuing that down here, I'm just checking it. So if you multiply this back out, you get back to there. Because 2 minus a squared is 0 in this context. So I was checking on these alleged factorizations, all right? Case 3, x squared plus ax minus 1 times x squared minus ax minus 1. You multiply it out, you collect like things die because the condition a squared is equal to minus 2 gives you that's 0, and back to x squared plus x to the fourth plus 1. So indeed, if there do exist if there always exist solutions in case 1, 2, and 3, an element a such that a squared is congruent to 1, 2, or minus 2 mod p, I said minus 1, I think I was supposed to say, then we can factor it. And in fact, that's the case, and the argument is pretty slick. Here it is. Consider the homomorphism from the group of units, basically non-zero ZP to non-zero BP divided by the squaring map, phi of x equal to x squared. All right, so it's pretty clear that it's a homomorphism, right? Because phi of xy is equal to xy squared, which is x squared y squared, which is phi of x times phi of y. So it's a homomorphism of the multiplicative group of non-zero integers mod p. The kernel, what's the kernel? Well, the kernel is the set of elements which squares to 1. And so the kernel of phi is equal to 1 and minus 1. So think about this. If p is greater than 2, then the order of the kernel of phi is 2. All right. If you let h be the image of the homomorphism, then by the first isomorphism theorem we have that ZP non-zero integers mod p mod the kernel is isomorphic to h. So check out this sneaky step. So ZP mod h, right, is isomorphic to ZPX mod ZPX mod kernel, but this is like, these cancel, right, and the reciprocal flips upstairs, basically, the unreasonable success of the quotient notation. So this is in fact isomorphic to the kernel. Aha! But the kernel is got 2 elements in it, right? So this has 2 elements, which means that there's the coset h and the coset xh for some x, which is not an h, right? And then, okay, so suppose minus 1 and 2 are not an h, all right? In other words, this would be like case 1, there's case 2. This, if we can show that neither of these things happen, it forces case 3, then we're done. Sneaky, sneaky. So if minus 1 and 2 are not in h, that means that minus h is equal to 2h, because again, there's only one other coset. So the non-h representatives must produce the same coset. And so minus h times h is going to give you h, because, well, minus 1 times minus 1 is 1, and 2 times h times 2 times h has to be equal to h, and what does that mean? Well, that means that minus h times minus h is equal to minus h times 2h, right? But that's equal to minus 2h, which is equal to h. Oh, so minus 2 is in h. Aha, so if minus 1 and 2 are not in h, that forces minus 2 to be in h. But remember that to be in h means that there exists an a for which a squared is equal to minus 2. Is there something happening here? Oh, yay. Okay. I mean, I'm glad another student has joined us in addition to the 20 that were already here. But so a squared is equal to minus 2, and now on the other hand, if minus 1 and 2 are in h, then that means there exists an a in ZP such a squared is equal to minus 1 or a squared is equal to 2. So in all possible cases, you have an element which fits one of case 1, 2, or 3, and consequently we can factor x to the fourth plus 1. It reduces any mod p. This problem, yeah. This problem is the stuff. You know, the thing that took me a second when I finally had a flash, I finally realized, like, the isomorphism I couldn't understand was coming from this. So, like, since ZP, the non-zero P mod kernel is isomorphic to H, where H is the image of the isomorphism here. I mean, the homomorphism from the multiplicative group to the non-zero multiplicative group of integers mod P. Well, because you have that isomorphism, ZP mod H is the same as ZPX mod kernel. And you can think of these as canceling, and that goes upstairs. And so, like, that's how we got that this has two elements in it, because the kernel has 1 and minus 1 in it for this map. So, yeah, this problem is, I mean, without the hint, without the hint, this problem would be totally ridiculous. But with the hint, it's just ridiculous. So, but I enjoyed it. It's important for you guys to have some hard problems here and there. That was 27. Move on to 28 here. Let's see here. I forgot what the problem was. I should have said more. Let D be square free. The norm is defined to be that. Oh, I was supposed to prove the properties of the norm, is what this problem was. Prove the norm of that the norm is 0 if and only if you got 0. So if the norm is 0, it means that this is 0, which means that that is 0, which means that a squared is equal to b squared d, which means that a squared over b squared is equal to d, which means that plus or minus a is equal to the square root of d. But that's impossible because d was square free, and you can't have a rational number equal to an irrational number. Thank you, Math 200. So I refuse to prove that in a higher class because I feel like you've already proved it in 200, so why should I prove it again? And anyway. And here's the multiplicative properties, just straight algebra, like beautiful algebra, but there it is. 17, we're supposed to write this cubic as a product of irreducible polynomials in Z2X. I factored by grouping, actually, and then I changed this to -1, the difference of perfect squares, you know. And then the x minus 1 is x plus 1. This problem has got, that one's fun. That one's fun. Everything seems fun after number 29. This one wasn't too bad. Let D be an integral domain. Suppose A is irreducible and U is a unit. That means, suppose that B is equal to AU. So we're trying to show that B is also irreducible, all right? So if B is equal to AU, if B is equal to B1, B2, then AU is equal to B1, B2, which means that A is equal to B1, B2 U inverse, right? Thus, B1, B2, B2 prime, where B2 prime is equal to B2 U inverse, but since A is irreducible, we find either, we find B1 or B2 prime is a unit. And so B is equal to B1, B2, and B1 is a unit. Well, if B1's a unit, and if B2 prime equal to V equal to this, that implies that B2 is UV, which is a unit. I don't know, I'm tired, but it's, if you didn't word it exactly like me, you might still be right, you know. That one's bad. Show that in the Gaussian integers, 3 is irreducible, but 2 and 5 are not. This is a nice problem because it showcases the point of studying the norm in here. So basically the norm of a plus ib is a squared plus b squared. And we also have this multiplicative property for the norm in this case, right? Like so if you suppose you have a reduction of 3, then that would be 3 is equal to xy. Well, that would be the norm of 3 was equal to the norm of 3, norm of x times norm of y. In other words, 9 is equal to the norm of x times norm of y. So either you got norm of x and norm of y are 3, or you got norm of x and norm of y is 1, or you got norm of x is 1 and norm of y is 1. Them's your possible integer solutions. These don't concern us because those would not ruin the irreducibility of 3. Because n of y being 1, n of x being 1, that means that x and y are units in those cases. So this is what we got to worry about. If 3 could be irreducible, it would have to have an x and a y that both have norm 3. But if you look at a squared plus b squared equal to 3, you get no integer solutions. Consequently, 3 is irreducible. So, yeah. I hope you guys don't mind if I don't write down the details of a squared plus b squared equals to 3 has no integer solutions. I could easily fill a quarter page and it wouldn't be understandable. And I don't see the point of writing it, so I just don't write it. Just be careful that when you say something doesn't have integer solutions that it actually doesn't. Because otherwise, it will be bad. On the other hand, 2 and 5 are equal to this and that, so yeah. And so basically that comes in part from this. This has norm 4. So you know you're looking for like something with norm 2, and here you know you're looking for something with like norm 5 and norm 5. So you think about like how can I get 2 or 5 from a sum of squares? And those things will be the components that you're looking for because that's the structure here. So like I know 2 squared plus 1 is 5. That's why I looked at 2 plus I. Yeah. This one is like an example in the text. It's a little bit trickier. 7 is irreducible, so I feel like I talked about this one in class. I don't remember. I think I talked about the example in class over here. But anyway, the norm of this would be a squared minus... Oh, this is like it. It's not the same one, though. A squared minus 6b squared would be the norm, all right? So what are the units, first of all? The units are those that give us plus or minus 1. The only way I can get plus or minus 1 from this combination is A is plus or minus 1 and B is 0. As soon as B is non-zero, I can't hope to attain 1 there. Or can I? Oh, wait a minute. There's more. Look, this is also a unit. Yeah, this actually has maybe infinitely many units. Yeah. This is one of those real quadratic fields. It's much uglier than the imaginary quadratic fields are much easier because you have like a squared plus b squared with some number. So you have finitely many solutions to that. Possible. Whereas when you get this minus, then you can get tons of units. I forgot about that. I guess it doesn't matter though. Suppose 7 is equal to x times y. And, the point is whatever the units are, they have norm 1. So who cares what they are actually? This is needless. In fact, if you think about the previous one, I didn't actually need to know that the units were plus or minus 1 in that example either. My analysis was totally on the level of norms. That was just an unnecessary extra little, hey, look at this. Anyway, so suppose 7 equals xy, that norm of 7 is 49. So we have to have both of these being 7. Now, if that's going to be 7, that means that we're looking for x, a plus b root 6, and y like that, such that a squared minus 6b squared is plus or minus 7. And u squared minus 6v squared is plus or minus 7. So mod 7, you can check there are, and here's the check, I actually checked it here, check it out. 1 or 4 or 9. Here's the cases, as you can see, only 0 works. So I actually wrote out the details this time. So A equals B equals 0 is the only mod 7 solution. And consequently, that implies that A and B are congruent to 0 mod 7. But if A and B are congruent to 0 mod 7, that means that A squared minus 6B squared has a divisor of 49, which is hard to do when it's equal to 7. So that's a contradiction, consequently. It's irreducible. Again, I am just wholesale borrowing the concept of example 2 on page 30, I can't read, 13 of Zagalian. Where are we? And finally, this is problem 121. So I just ran the division algorithm for 12 plus 3i and 6 minus 9i. And after, yeah.
So you get 0, but I thought that meant that negative 3i would be...
Oh, when I get 0, that means that, the step before it, yeah.
Okay.
Yeah, but if you follow the steps, it also gives you a way to construct a linear combination of them that gives you 0 as well, for what it's worth. I mean, every one of these slots has information about how to obtain these numbers in terms of combinations of alpha and beta. But the most interesting one is this one, because minus 3i is equal to beta minus 2 times alpha minus I beta, which, yeah, you can ignore that. And of course, you could say that the GCD is minus 3i. You could reasonably say that the GCD is plus or minus 3 or plus or minus 3i here. In fact, to say it more properly, you should say that the GCD is an ideal. And it's the ideal which contains plus or minus 3 and plus or minus 3i. But we didn't quite get to that level of thinking in here, which is fine. So there's that problem. dB of PID, principal ideal domain, P an element of D. Prove that the ideal generated by P is maximal ideal if and only if P is irreducible. So let's see here. If this is a maximal ideal, and if I suppose I have P is equal to x times y, right? Then for each r, P times r is x times y times r. So that means that this is an element of the ideal generated by x. Consequently, P would be a subset of the ideal generated by x, right? Which would be a subset of D. But by maximality, we find P equals to x, right? Or x ideal generated by x equals to D. In those cases, right, that's exactly what we need to force one of the factors to be a unit. So in case number 1, if P is equal to the ideal generated by x, that means that x is equal to PR prime for some r prime in D, which means that P is equal to x times y, which is also equal to PR prime. See here, why do I have P is equal to xy was at the assumption at the start. But that tells me that, why don't I have, I'm missing something here, guys. Sorry.
We have that P is equal to xy, and then we have that
Oh.
PR prime, so...
Right. Oh, right. So, I'm sorry. Just this and that imply that r prime y is equal to 1. I was trying to see this implication from that middle equality, and it was going, I was not getting it. So if that's the case, y is a unit. So it's not a reduction. It's still the irreducibility of P is safe if y is a unit. Okay. And then case 2, if x is equal to the whole shebang, that means that there exists an r prime such that x times r prime is equal to 1, which means that x is a unit. Because it has to hit 1. If it generates all of D, it generates the unity, which is in there because it's an integral domain. Because if it's a principal ideal, it's an integral domain in which every ideal is principal. What I said. And then, so in either case, we get a unit in p equals x times y, which means that it's irreducible. And there's the forward implication. Conversely, assume p is irreducible. If p is irreducible, consider an ideal between the ideal generated by p and D. If you look at, since D is a PID, that means I is equal to an ideal generated by x for some x. And if you look at those inclusions, what do they tell us? They tell us P is in here, which is in there, which means that P is equal to x times r, right? Consequently, x is a unit. How do I know that? Ooh. Oh, because P is irreducible, right? So here's a reduction. It's a factorization of P, so that means that, you know.
So x has to be a unit because.
Yeah. So
I guess R could be.
Yeah, couldn't R be a unit too? Yeah.
Because the unit is.
Let's see here.
Yeah, we need either x is a unit or R is a unit.
Right. Oh, or R is a unit. I think my wording is weird here. Or R is a unit, in which case you get that P is equal to x. So that means that, but you're just with P. So depending on whether x is a unit or r is a unit, you either get that P is equal to I or you get I is equal to D, which shows that it's maximal. But admittedly, my phrasing here is not good. I should take off a point, at least. This one's easy. 1 minus I is irreducible, so the norm is 2, which means that either one of them, the other is 1, which means that every factorization has a unit. Yay. 19. If P is a prime, which has the form a squared plus b squared, then a plus ib is irreducible in the Gaussian integers. Prove that find 3 primes that have the property and the corresponding irreducibles. All right, right. So suppose we have a prime that has the form a squared plus b squared. Well, then the norm is equal to a squared plus b squared, right? And that's equal to a prime. And if you think about a plus bi being the norm of x times the norm of y, well, that means that p would have to be n of x times n of y, right? So either n of x has to be 1 or n of y has to be 1 because it's a prime. So by Euclid's lemma or whatever you want for integers, one of them or the other has to be 1, which means that either x is a unit or y is a unit, which is to say that a plus bi is irreducible. So we're taking the existence of the prime, that's a sum of 2 squares, and we're saying you take a complex linear combination of those numbers, and that's an irreducible in the Gaussian integers. And there are, of course, many of these. In fact, this one already showed up in a previous problem.
Yeah.
That was the reduction of 5. The reduction of 13, something like 2 plus 3i, and minus 2 plus 3i, and 17 looks like this. And those are the corresponding irreducibles. Yeah. This one's nice. Sorry to go a little bit over. I just want to finish before we're almost done. Prove that this forms a prime ideal. So here we have even coefficients, right? So I thought about this problem, trying to do it directly, just picking, 2 things such that the product is in the ideal, and then showing that, if you take the product of two polynomials with even coefficients, it must be that either, a of x or b of x is a polynomial with even coefficients. But it quickly was clear to me on the basis of the previous problem that was like this that I shouldn't do that. It's not a good idea. It's going to be very hard. So we have to use theory. So the basic point here is to notice that I equals to 2z is a prime ideal of z. So, in other words, x times y, an element of the evens, means either x is even or y is even. You know this. And moreover, I of x is 2z times z of x. It's 2zx, right? So by number 38, which we already worked, we find that this being prime implies that that's prime. So it's actually just the application of the previous homework problem. Here's a standalone proof. You look at the homomorphism, because on the test you might not be able to refer to a homework problem, for example. So if you look at the you just define this isomorphism, it's the quotient map. You just take each coefficient and map it to its coset mod 2. It's z2 coset, like so. That gives us a ring homomorphism, and the kernel of this ring homomorphism is exactly the polynomials with coefficients with even coefficients. But then, by the first isomorphism theorem of rings, we also know that z of x mod 2z of x is z mod 2z of x. I mean, well, this is by the first. I mean, this is the kernel of psi, right? This is the image of psi. You can prove that this is a surjection because, it's pretty obvious. If you take this arbitrary element in z mod 2zx, well, what maps to it? This. So, like, the formula is almost a proof of surjectivity. And consequently, we have this is isomorphic to that. But remember, we know that this is a prime ideal because 2z is a prime ideal. Excuse me. How do I say this? We're in an integer. We're in a. No. Not what I want to say. This mod that is an integral domain because I'm forgetting the logic here. Goodness gracious. Oh. Oh, here we go. This mod that is a field, right? That implies that this is an integral domain because if you look at polynomials over a field, it's an integral domain. So the fact that this is isomorphic to that means that this is a integral domain, right? Because that's an integral domain. And if this is an integral domain, we're saying z of x mod something is an integral domain. Therefore, by our prime ideal theorem, that means that if the quotient's an integral domain, then this is prime. The other theorem we have like that, of course, is if the quotient's a field, if and only if that's maximal, right? So those are the hero in these kinds of problems. Please let this be the last problem. Yes, it's the last problem. I'm tired. Until tomorrow, of course. But so express both 13 and 5 plus I as products of irreducibles and z mod I. The Gaussian integers. So 13 was easy because it's 4 plus 9. So I just got to think about, how can I get. So there's a lot of choices here because you could do plus or minus 2, you could do plus or minus 3i. But I just thought about it. I knew I wanted something real. Yeah, what's that? I get. Oh, you got this one? Yeah, I guess that one's actually, I'm saying too much there. That one's clear on the basis of earlier patterns. This one requires a little bit more tinkering. Here's how I thought about it. Let's see here. Oh, I'm just proving they're irreducible. I forgot. This is got a norm of 26, right? So you're looking for something with norm 2 and norm 13. So norm 2, you got choices like basically plus or minus 1, plus or minus I. To get norm 13, you're looking at stuff like plus or minus 2, plus or minus 3i, you know? So I decided for 1 minus I and 2 plus 3i after some scribbling. Because when I multiply this, I get 2 minus 3i squared, which is 2 plus 3, which is 5. And then I get a minus 2i plus 3i, which is plus I. But that's how I knew to look for that. I was looking for something with norm 2 and norm 13, so that greatly reduces the tinkering.
Yeah, I did way too much tinkering.
So basically the thing was I had to decide 1 minus I versus minus 1 plus or minus I, or 1 plus I and 2 plus I versus minus 2 plus or minus 3i. And I still may be not giving you an optimal way of thinking about it. I mean, maybe there's something even more insightful that just immediately lets you write this down. But this isn't too much thinking what I was doing, so like I'm pretty happy with it. I also had a chance to talk to my brother about the homomorphism problem. Like, you know, we listed the possible additive homomorphisms, and then we used multiplicativity to train it to you know, pin it down further. And I was hoping he was going to tell me, "Oh, you idiot, there's blah 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 blah," but basically he's like, "No, that's just kind of it." He's like, "There's just kind of ugly number theory problems." I'm like, "Oh, okay." So I think we did it right. It's just tedious.
Yeah.
Do you have any other questions?
No.
Actually, do you have any questions? To start with, I was looking at ones and I was like, wait a minute, we already did this one. I was like, it took me a while to figure out where to start. Anyway. Look at all this trigonometry over here.
I know.
It's something to behold.